Hello, it's a pleasure and an honor to be back to present at FlowCon 2022. Today I'll be talking about the topic of science and security. And this presentation is the fourth in a series of so many years of presentations on the topic of cybersecurity data science, a field which has grown rapidly in this time and which I've been pleased to be able to talk about and track it as it grows. And also proud that recently this has resulted in a book published by Springer, which could not have been possible without the help and contributions of members of the FlowCon community. And in particular, I'd like to thank the CMU SEI for their help and support in bringing this publication to fruition. In particular, Dr. Timothy Shimao had provided a foreword to the book, which recognizes the collaboration and support which FlowCon has given this research. So today, the topic will be about the involvement of science and scientific methods in the cybersecurity field. And one of the results of the research that is brought up in the book is that data science offers a lot of methods for analyzing data, of course, but that the scientific aspects that are brought to bear are still something in development and under debate to some degree. And part of this is that the field of data science itself is still evolving, and that there are debates about the amount of scientific rigor in the field of data science. So when we talk about cybersecurity data science, certainly there is a great deal of engineering and methods for data analysis. But one of the things that was brought up in the research and in interviews with practitioners was that there's not a great deal of theory or theoretical discoveries being generated through this field. And that's something that ideally should happen more in the future. So today, my goal is to talk about science in the security field, hopefully to avoid some pitfalls. One of those being to bore the audience and to go too far into the details. And the other is to avoid falling into tropes concerning science, which is to delve into the notion that all scientists wear lab coats and are playing with test tubes. And as it is today, we are aware that some people get very passionate about the topic of science, and there's big debates going on about what exactly constitutes science. So the hope is to also avoid offending anyone and to stick to the facts. And so that's what I'll do, which refer back to the research in the book. And first, by presenting and framing this topic of security science, and to attempt to, in particular, distinguish engineering from science. And then, in a practical respect, talk about science as a process, which I think is the best way and the best hope we have for involving scientific methods in security. And then to talk about how that can be operationalized, and then some of the hope for the future. Again, based on the research, which itself had involved interviewing 50 cybersecurity data scientists worldwide. So to start things off, I'll talk about the science of security from a general perspective. And one of the key things that came out of the research is the amount of growing complexity in the field, the proliferation of networks, but also surrounding technologies, which has really invalidated the traditional notion of a castle and moat paradigm for protecting networks, which is that there's a great deal of complexity now, which makes the job of the security professional that much more difficult. And indeed, we can say that in many cases, there may be the barbarians may be inside the gates because there's so many ways of tunneling into networks and of residing in networks across boundaries. and that cybersecurity data science has brought forth a number of methods for analyzing data to help gain insights into this complexity, which is very promising. And so this is already a very fast evolving field, and there are practitioners out there dedicated to using data analytics and data science for security. However, one of the things that was raised in the research is that there are natural limitations to engineering-based approaches, which is that the amount of algorithms that can be thrown at the problem will not overcome fundamental security challenges absent efforts to gain insights into fundamental behaviors and to understand complex phenomenon, which engineering cannot solve by its own. So in particular, when we're talking about very complex phenomenon, there are often great unknowns. So this implies that there needs to be inference, which is gathering of evidence, using that evidence to develop theories and hypotheses which bear upon phenomenon, and to continue this cycle of discovery. So in a sense, with security engineering, this is done in a very practitioner-based way, but one thing that was raised in the research is that a lot of cybersecurity data scientists feel that this can be operationalized much better, that it can be standardized and made replicable so that we can pursue and share theoretical findings in a community setting to realize deeper insights. And so this is part of a discussion that's actually been going on for some time. And there's been a number of research publications and groups and communities of interest that have been discussing security science. And in particular, I ran across a NSA Next Wave issue from 2012 that focused on this topic. And there were some very good and very insightful and provocative articles from a range of security researchers who questioned to what degree is science being pursued? And the answer was, well, not very much, and that much more could be done to improve rigor and to improve approaches to bringing science into security practice. So one of the things then this points to is the degree to which the security field is heavily oriented towards engineering, and how can that be distinguished from the effort to do science. So one metaphor I like to use, it helps to have a physical metaphor, is to think about airport security. And if we think about efforts to conduct security monitoring as having to process millions and millions of customers, sometimes every few seconds in a network, and to allow them to go through when they need to go about their business, but to recognize the exceptions to some degree such that we can stop the bad actors. And so the one, if you'll allow me this one indulgence, I will delve into a very theoretical aspect here and to propose that this is not too far from what's known as Plato's allegory of the cave, which is that in discussing our appreciation of complex phenomenon or the world, as Plato framed it, we're often beset by seeing shadows on a wall, which is Plato's allegory proposes that, in a sense, we're all trapped in a cave, and that behind us is a fire, and there are puppets that are being paraded before the fire, which cast shadows on the wall. And we try to interpret these shadows in terms of interpreting the real world. And I think this is an interesting allegory because it does point to the amount of complexity that's developed in the security field, that there's so much going on and so much complexity that often we are looking at shadows and trying to interpret them. So we can wring our hands about that as much as we like, but one of the things that was brought up in the book was to look at prior art. and other fields in terms of what they've done to try to deal with very complex situations where there's unknown unknowns and to try to make sense of those. So one of them, of course, the most well-standing and most formalized is the medical field, which I think offers some very good tips to us in terms of how to segment the hands-on operational what's called clinical practice, which is the operational practice of medicine in the hospital, dealing with patients, versus the research aspects, which is often a very more regimented and structured and rigorous approach done in research hospitals, often using statistics and very rigorous methods to try to ascertain root causes, as opposed to the clinical experience, which is often based on individual expertise and intuition. And in this respect, one article that I ran into that I found resonated very well with the security field, which I can recommend, was an article dating back to the late 80s, actually, studying clinical versus actuarial judgment. And so these terms, again, map quite nicely to the medical field, but I think are applicable to the security field, whereas clinical experience is that experience that's based in the field and is often involves making judgments based on intuition, whereas what's called actuarial judgment is considered to be empirical or statistical, where there's very rigorous methods and there are controls put in place to try to analyze evidence in a very structured way. And so one of the findings of the article is that the actuarial method often is demonstrably better at helping to track and understand complex phenomenon, as opposed to intuition alone. And this, the article I think is quite nice in saying that the two actually should ideally work together in the same way that it does in the medical industry. The medical field is that there's a collaboration between the two, that medical research informs clinical practice, and that clinical work can involve gathering evidence and bringing it to bear for the purposes and use of medical research. So we have aspects of this, of course, evidenced in the security field, which is that often in an operational setting, there's an effort to explore using data, phenomenon to look for patterns, to set up rules, to even use machine learning models to detect cases of security violations, then to look at the results and hopefully then to feedback those insights to improve practice. And this is already done and is done as a matter of course in operational settings. And I believe the research points to, from the interviews, that what can be done is to better operationalize this, that it's often done in an ad hoc way, and that what can be done in the future is to make the science more of a process, to embed this process of discovery and leading to improved models, leading to improved operational practice in a cyclical way. So if we come back to the metaphor of the security in the airport, we see that there's often exceptions. So there's police officers traveling, people traveling with babies, people who have a legitimate reason to carry a weapon, or people who are carrying medical samples. And so that these people are known exceptions. And this is one of the great challenges of security, also cybersecurity, which is there's systems administrators, there's pen testers, there's people doing large-scale systems development who often trigger alerts as part of their role, who need to be let through and to continue their work, but they often give off signals that would appear to be a security violation. So part of the big challenge is how to operationalize those insights into valid roles that are unusual from those which are parading or who are appearing to be doing things and have no reason to be doing those security violations. So cybersecurity data science as a field has this whole toolkit of different techniques that help us to understand phenomenon, everything from doing unsupervised pattern analysis to looking at graph network patterns, to extracting features from large data sets, to then doing statistical diagnostics, and to putting in place predictive models. So there's this rich toolkit that has been developing over the last 10 years to help us do this. And part of the results from the research in the book have suggested that in order to grow as a field, that there needs to be a better orchestration of three core aspects of cybersecurity data science to bring better operational science into practice. And one is to become better at data management practices, to improve the use and application of scientific processes in the field, and to stimulate and ensure and incentivize cross-domain collaboration between those who are conducting security monitoring, those who are doing data analysis, and those who are managing processes, and those business stakeholders who are using infrastructure. So if done correctly, one of the major implications is that there is a more operationalized approach to feature engineering. When that data is coming in, that there are efforts to develop raw data into features which can create models and then insights, and that this is a continual process, that there's an aspect of exploring raw data continually to develop new models, but ideally that the models that are developed become categorized and inculcated in systems so that they lead to automation. And that getting that right is the secret sauce of cybersecurity data science, that operationalization of exploration and discovery leading to detection and automation is the holy grail, and it's the difficult thing, and I think that's where the scientific aspects help. And we can't really speak of the scientific aspects without pointing to people. We have these sophisticated tools, techniques, methods for doing data analysis, but essentially what we need to ensure is the interaction of different roles in the security process, and that there's a valid feedback loop, which involves sharing information and sharing insights between different domains of expertise, and that this is in some ways the hope and the way forward for cybersecurity data science is the operationalization of data that's oriented in scientific methods towards achieving insights which can be operationalized. So concerning the operationalization of security, we can say that it is a cyclical process, and ideally it is embedded in the incentives and the collaboration between different roles in an organization, and that it involves combining exploration, discovery, and insights with pattern detection for automation. So it's very appropriate to say that a pseudo-scientific approach is already part of most security operations, in the respect that models and rules are developed and that new observations lead to improved methods for detection. However, one of the points that was raised in the research in the book was to recommend that we have a much clearer and differentiated understanding of the application of different techniques in terms of what's being achieved, and that in particular with machine learning, there's a risk of over-relying on correlation-based observations, which is that with supervised machine learning, often the observations are based upon aggregated algorithmic-driven correlation, as opposed to understanding fundamental explanations of underlying phenomenon, which involves explaining the involvement of different variables and how those contribute to some particular phenomenon so that we can build more fundamental understandings that can lead to covering rules that can be used to improve detection at a more fundamental level, and in particular to associate and understand that there's different layers and levels of the application of analytics in the security field, some being focused on the equipment and infrastructure, but equally as much and more important these days is also understanding the economic aspects, risk in terms of what equipment is most at risk, and how economic behavior is very important to cyber phenomenon, and also behavioral human aspects of cyber attacks and cyber behavior. So machine learning has really advanced some of our ability to pursue this cyclical scientific model, which is particularly the combination of unsupervised machine learning with supervised machine learning, if done in a cyclical respect, can help us to identify categories for tracking, and then to improve supervised machine learning models, and then to feed this back to better understandings of raw pattern analysis. However, again, this is often based on algorithmic correlation. And one of the things that is suggested is that we could get better at applying some of the classical scientific methods to the treatment and analysis of data. So I can recommend a very good book here on research methods for cybersecurity, which breaks down 4 key scientific methods in the cybersecurity field that can be applied for rigorous analysis of data. One of the great perspectives that's given here, I think, is the notion that perfect is the enemy of good, which is that we can become trapped in this notion of science as being white lab coats and test tubes and experimental analysis done in a controlled laboratory setting, whereas science can be conducted in less rigorous environments, and as long as one's connecting data to insights in a rigorous way, that we can pursue scientific processes without necessarily being in a laboratory. So along with this is a broader notion of what constitutes evidence. And one of the implications of the research is that there's a large set of evidence which may be not being collected in a rigorous fashion in the typical operational setting, and that we can perhaps reconsider what might constitute evidence for scientific analysis in typical operational settings. I think one good example that I see often is that when a red teaming or pen testing exercise is undertaken, that often that results in insights that lead to restrictions or new rules. However, there's not often an effort to gather labeled data on the attack or the incursion as labeled evidence for detecting and associating with other potential attacks, so that, for instance, the results from pen testing and red teaming exercises could be used to train machine learning models for detection, and then to test those models and improve them over time in a scientific aspect. And so I think that's an example of where a broader view of the potential of collecting evidence can help us. And so there's evidence that this is already happening from the interviews that were done through the course of the research, which is the cybersecurity data scientists in the field reported using methods, novel methods and novel domains, and bringing those learnings into the cybersecurity domain. And through that, implementing rigorous methods that have been applied in other domains to gain insights. So for instance, in the area of fraud analytics or medical research, bringing those techniques to bear in a security realm in a more rigorous way. And that some of this is already happening, and this effort to bring in adjacent methods and adjacent domains into security research is bearing fruit in terms of helping to bring in new insights and new rigor. So now heading towards the conclusion here, there's the notion of where do we go from here, which is that it might be worthy to put out a type of broad proposal that I think we perhaps don't even understand some of the core fundamentals that we deal with in the security domain, such as what is a user in the theoretical aspect, what is our theory of a user in terms of the modern user who's interacting with many different devices, who may be being mediated through an app or a decision-making algorithm on modern infrastructure, and devices which are routing and making decisions on behalf of the user, that the actual human user in often cases is obfuscated, and that we could perhaps revisit and develop a theory of the modern cyborg user within complex cyber architectures, and study that and propose a theory of the modern user. And that in order to do that, we can adopt this cyclical approach to bring in scientific rigor into the analysis of data as evidence in order to build up models, which leads to learnings, which we can then propose and share in community settings, and in order to replicate and share insights that can then be improved. So the big conclusion from the book and the research focused on these three core pillars, and there were particular points made about each of these three pillars of data management, scientific processes, and cross-domain collaboration, about how we can improve practice in these three areas. It's not in scope, I think, today to go into the details of all the different points of advocacy that were made, but I did put in the appendix of the slides the detailed advocacy that was made in each of these domains, which is one of the major findings from the research in the book. But these are some of the high points, I think, that point out how rigor can be brought into the security realm in each of these areas through cybersecurity data science as a mechanism. So with that, I'd like to thank you. This topic has been very interesting, and this is the fourth presentation, and it's the one that has culminated with the publication of the book and the research. And I thank again the Software Engineering Institute and Carnegie Mellon University and the Flowcon community for its support and participation and help in bringing the research to fruition. And I look forward to continuing the discussion. Thank you very much.
Okay, some really good questions coming in for Scott, so let's get right to them. The first one, Scott, we have for you is, how do we balance the knowledge of the phenomenon, understanding security and data science techniques, thinking that cybersecurity and data science increase all day?
So yeah, that's a great question, and it falls into the category of how do we scientifically study phenomenon that's in flux. And I am a believer that we can certainly study things that are changing rapidly. I think we have to. So COVID's an example. And it's appropriate to say that one of the ways to do that is to isolate the constant elements. And I think one aspect that's constant in cybersecurity is people, and something perhaps we don't pay enough attention to. The interviews that I did that are reflected in the book indeed show that some of the cyber data scientists out there are borrowing quite a lot from the fields of fraud analytics, from criminology, and from economics. So they're applying social science methods to cyber, which I think help to give a different perspective. And one of the points made, I think, is that cyber is increasingly not only a technical phenomenon, it's also behavioral and economic. So it's perhaps in the economic and the behavioral aspects that we can gain a constant view on technology, even though the technology is shifting and changing and growing.
Great, thank you for that. Next, we have from Sam asking, did your research find any lessons in other disciplines that can help us defenders deal with the problem of having incomplete control over endpoints? He also mentions, for example, a large SaaS vendor with millions of users of their no-cost service can't track down every last user to conform malicious activity on their account.
Yeah, thanks. That's a great question. So last year I gave a presentation, which might be worthy to take a look at, which was about some of the methods that these cybersecurity data scientists were applying from other fields. And so epidemiology is an example. So when you're doing public health, again, you can't control everyone's activities. So you have to use inferential statistics and use techniques that can gather a good enough picture and act on statistical evidence. So I think that was one of the findings from the book, from the research, that there was the application of findings and methods from the fields of medicine and the social sciences that had methods that are able to deal with uncertainty to a better degree. And even when there's a great deal of uncertainty, for instance, on endpoints, to collect indicators. And I think that's points again to the science, is gathering evidence, even in small amounts, say, a 0.1% of users on the endpoints, and correlating what data is available from the endpoints with activities in order to make assumptions about what the greater population is doing. So inferential statistics. Mm-hmm.
Great. Next one we got, Scott, is the unpredictable human element is the perpetual stumbling block in cybersecurity, I think. Can you speak of the inclusion of psychology, human vulnerability that leads to security lapses in machine learning models?
Sure, yeah, and there's been some formal writings on this. So Oxmith's threat actor profiles, I think, are appropriate, and they frame people as rational, if misguided, in the types of incentives they're following when they're implementing attacks or cybercrime. And I think that's where economics can help us, is to realize that threat actors are human, and they act on incentives. So even microeconomics can help us to assess to what degree they will abandon an attack when enough of a threshold is put up that it's too costly in terms of their time or resources to invest in a particular attack. And in fact, one of the scientists that I interviewed indeed made that very comment. He said that essentially we're fighting a game of trying to make things inconvenient for attackers. And so while a great deal of the human behavior aspect is uncertain, developing personas and attaching concepts of incentives to each of the personas, and then developing countermeasures to counter those incentives can be quite an interesting way to approach this. And that's more in the realm of fraud analytics and criminology.
Scott, thank you again for your presentation. We thank you for your many years involvement in FlowCon here. I think it's a great testament that the book kind of started here at a FlowCon. So I think it's a great story. Thank you for your time.
Thank you very much. Thanks, Shane.